Hello and welcome back. In this presentation, we're going to look at the method of initial and average rates of reaction, and we're going to apply it to clock reactions. So you might remember that we can work out the rate of reaction by taking the gradient of a concentration time graph. And we could even work out the initial rate of reaction by taking the gradient at the start of our experiment. If it wasn't a flat line, we could take the gradient of the tangent line that is drawn at that point. Now, another thing that we could do is we could plot a rate concentration graph. Now, a rate concentration graph looks at what the changing concentration is and plots it against the concentration. Now, in that case, if the reaction is a first order reaction, then we expect a straight line, that the higher the concentration, the higher the rate of reaction. And for any particular concentration, we could work out what the rate of reaction would be. In fact, on this graph, we can see that the rate of reaction on the left is equal to some constant equal to the gradient of this line multiplied by the concentration of X. Now, this is true because this is a first order reaction. But this basic idea that we can equate the rate of reaction to the concentration is something that we need to be able to remember and understand and use in a clock reaction. So now let's go over and have a look at perhaps the most famous example. Now, say for example, we weren't measuring the concentration with time of a reaction, but we were using some other indicator to tell us what the rate of reaction was. Well, a clock reaction is one of those reactions where we use a visual change that's normally quite sudden to be able to figure out how long it has taken for the reaction to take place. Now, you can probably figure out that if the reaction has taken a very long time to happen, then the rate of reaction must be pretty low. In fact, we can work it out because 1 divided by the total time for the reaction to occur in is equal to the rate. And then as soon as we know the rate, we can now use that in a rate concentration graph. Now, perhaps the most famous clock reaction is the iodine clock. And we're going to talk through an example here. It's the persulfate version if you want to look this up somewhere else. But how this basically works is we have some colourless liquids that eventually turn a bluish black. To my eyes, it looks black, but it's often described as a blue complex. Now, this is because there is iodine reacting with starch, and we all know from biology that the test for starch is we add some iodine, it'll go blue-black. Now, if I put starch and iodine in this beaker together, it would go blue-black straight away. But what we can do is we can add another chemical that delays that process. So let's just talk through the reaction first. Now, I must stress here, this is often used at this point because it's just a very good example of how to process data to understand the rates of reaction. What is physically going on in this reaction is of less importance, but we'll gain some sort of understanding and then we'll at least feel comfortable with what is physically occurring. It involves 2 processes happening in our mixture of liquid. The first is the production of iodine. And the way that works is when we get something like potassium persulfate or something like that, and the persulfate ion, the S2O8 2-, goes and meets some iodide ions. Why are the iodide there? Because you've probably got something like potassium iodide in there as well. But in solution, those ions are all floating free. Now, those are both colourless liquids, and especially in solution, which means that what happens is it undergoes a reaction, the 2 iodide ions join together to form iodine, and it leaves a sulfate behind. Now, that iodine would turn the starch blue-black straight away, were it not for a second reaction that takes place. And now that reaction is formed from the introduction of a second chemical. So let's have a look at that one. You see, what we've added is something like sodium thiosulfate. And the thiosulfate ion, the S2O3 2-, actively attacks the iodine that's freshly formed. It means that while there is still thiosulfate ions in this solution, you won't see the iodine reacting with the starch to form the blue-black mixture. It's only when the thiosulfate is all mixed up that iodine can then persist to react with the starch and form the blue-black mixture. Now, what we can do in this experiment is we can vary the concentrations of the main chemicals and time how long it takes for this reaction to complete. 1 divided by that time will give us the rate of reaction. Now, a really important thing in this reaction is not to get too concerned about what the iodine is doing with the starch at the end. That's just an indicator that the reaction with the persulfate has finished. Now, what we could do is we would like to investigate what the effect of the concentration of the original persulfate might be and the concentration of the iodide might be, the original ingredients of this experiment. So we would understand that the rate of this reaction would be equal to the negative change in the concentration of the persulfate per unit time, which basically, written out using a rate equation, would be that there was a constant of proportionality, the rate constant K, multiplied by the concentration of the persulfate, the S2O8 minus ion, to the power of m, because we don't yet know the order of that reaction, and also multiplied by the concentration of the iodide ions to the power of n, because we don't know what the dependence or order this reaction has to the iodide ions. Now, how do we proceed when there are so many things unknown? There are 2 orders here that we don't know. The rate of reaction we don't yet know, and we don't know K. Well, one of the things that we can do to make this easier is we can plot log-log graphs. Now, before, when we did log-log graphs, we used log to the base 10. We could also use the natural log. It works exactly the same. We just have to remember which one we've used when it comes to rearranging. Now that means if we take the natural logs of everything on the left and the natural logs of everything on the right, that's consistently the same. So the natural log of the rate of reaction is going to equal the natural log of the rate constant K plus m multiplied by the natural log of the persulfate concentration plus n times the natural log of the iodide concentration, and it should produce a straight line graph like this. But there are still things in this that we don't know. 2 things are simultaneously changing. So what we need to do is we need to isolate one and change the other. So, for example, if we ran this with different concentrations of persulfate whilst keeping the concentration of iodide the same, then basically everything in the n natural log of iodide would just be constant. It would be the same every single time. So what you can see here is that the natural log of the rate would be equal to the natural log of the rate constant plus m natural log of the persulfate ion concentration plus a constant. Now what we could do there is we could plot the natural log of the rate versus the natural log of the concentration of the persulfate. It's worthwhile remembering that lnk, the natural log of the constant, plus the constant which is to do with the iodide, that is all a constant in this, and so it will just come out as the intercept of the log-log graph. But the thing we're trying to get, and why we do this, is we're trying to find m, which is the order of the reaction with respect to the concentration of the persulfate. So by freezing out the iodide and keeping the concentration the same, we can look at how the rate of reaction is dependent on the persulfate. And that is what this process is doing. Now that's the first step. We now need to look at the second step. Well, we know a little bit more, but we don't know everything. For example, what we do know is how the rate of reaction depends upon the concentration of the persulfate. We also know the order of that reaction, m. But what we know nothing about right now is how the rate of reaction depends upon the concentration of the iodide. And we don't know what the rate constant is for this reaction. So there's still 2 more pieces of information that we're trying to get. Now what we can do is we can do the same process again, but this time we're going to freeze the concentration of persulfate and we're going to change the concentration of the iodide. This enables us to investigate what the relationship is between the rate of reaction and the concentration of the iodide. So we do that. We plot a graph of the natural log of the rate of reaction. It's going to be equal to the natural log of the rate, which we don't know yet, plus a constant, which was where the persulfate was, plus n natural log of the iodide concentration. So plotting the graph of the natural log of the rate versus the natural log of the iodide concentration will now give us n, which is the power to which the concentration of iodide had to be raised to make it proportional to the rate, which basically means n is the order with respect to the iodide concentration. So now we know another thing. We now know of what order both the persulfate concentration has to the rate and what the iodide concentration is to the rate. And you can see in bold there, I've showed you basically everything we now know. The only thing we now do not know is lnk. So how are we going to find that out? Well, basically, we know everything else. And it's worth noting here, if you've forgotten, how did we know the rate of the reaction? And remember that rate was 1 over the time that it took for the reaction to take place. So we can just time that directly from, how long it took for it to go blue-black. Do 1 divided by that, that gives us the rate. We also know the concentrations that we're using. For example, we'd know the concentration of the persulfate, and in one of those experiments, we'd also know the concentration of the iodide. We know the orders of power, m and n. So really the only thing we do not know when we put data into this is lnk. So what we can do is we can put all of those numbers in from our data and work out what the order of this reaction is, and we can also work out what the rate constant is for this reaction. Now, there are obviously some sources of error in this process. We're making a big assumption that the rate of reaction is constant. We're actually making assumptions that it's first order in this whole process. In taking that the rate is 1 over time, we're suggesting that the rate does not change in that time interval. We're actually taking an average rate over that whole time, which is fine, except if the rate is substantially changing in that time interval. So, for example, look at this. If I had the reaction conclude after 1,000 seconds, then yeah, the gradient of the concentration time graph is pretty much equal to what the concentration against time data is showing in that space. So you can see there's kind of good agreement. The reaction rate is very, very similar to the tangent at that point. But if I had the reaction go and take place and was much longer, then what I'd now find is that for substantial periods of time during that time interval, the reaction rate was different to the theorized reaction rate as found from the tangent line by itself. So what we find is that the longer it takes for the reaction to take place, the more the chance that the reaction rate wasn't constant throughout the entire reaction. So what we want is rapid reaction rates that take place in a matter of seconds and with high concentrations. And then the accuracy of this experiment is going to be much higher. Now you might find that everything we've just said went past in a bit of a blur. This is really complicated stuff, and you might have to go back and look at the last couple of slides again before you can make any progress with this task. I'll try to give you an explanation of the task, give you a little bit of help of how to proceed through, but if you don't need it, just pause it here and see if you can process this data. Right, okay, everyone that stayed behind, let's talk about how we do this. So what have we got? Well, we've got 2 sets of data here, and basically in the first set of data, we've kept the concentration of the persulfate the same, and we've changed the concentration of the iodide. And we're looking to see how long does it take for this solution now to change colour. And so we've got all of these iodide solution concentrations, and we've got the time that it takes. Now in the second set of data, we're keeping the concentration of the iodide the same and changing the concentration of the persulfate, changing the concentration of the other chemical in this, and again looking at how long it takes for this reaction to occur. So what do we need to do to process this data? Well, the very first thing is you need to calculate the rate. Now you know that the rate can be calculated by just 1 over the time, and you see the time is in that second column. So for the first row, it would be 1 over 40. That would give you the rate of reaction of that first line. So go do that and add the rate of reaction to each row. Now for that first set of data, remember that if we froze out and kept constant the concentration of the persulfate, then all we now are interested in is to see how the rate of reaction is dependent upon the concentration of the iodide. So doing a log rate versus log concentration of the iodide would give us the order of the reaction n from the gradient of that graph. So plot that first. And now having plotted that, we need to now plot the other one to find out what the other dependence is. So now you're going to need to plot the natural log of the rate versus the natural log of the concentration of the persulfate to work out what the order of that reaction is. The third part of this is now writing this out as in rate equation form. So you can see that the ln of the rate is going to equal to ln k plus n ln the concentration of the persulfate plus n ln concentration of the iodide. So if we know that line, then what we could write that out as just that the rate was equal to k concentration of one to a certain power multiplied by concentration of the other to a certain power. See if you could write that down. Final step, with any data from this table, can you substitute that data into this formula to calculate what the rate constant k would be for this data? And from the overall order of this reaction, can you also work out what the unit of k would be?